In this video I want to start a series of videos on exponential growth and decay. To introduce this subject, I'd like to consider this very basic problem. Here we are given a bacteria and we want to model the growth of that bacteria with a function, given that the population size that we start with is 1 and the population doubles every day. So these conditions are pretty simple, yet sufficient to, I think, start thinking about the idea of population growth. So to start, since we want to come up with a function, let's just think about points on a graph, that the graph of that function is going to have to pass through. On the vertical axis, let's put the population size, and let's represent that with P of t. And on the horizontal axis, we'll represent the time with the variable t. And here, t is going to be in days. The initial population is 1, so when t is equal to 0, when we start, the population is 1. Right, so our graph should have the point 0, 1 on it. After 1 day, the population doubles in size, so our graph should also have the point 1, 2. And then at the end of day 2, that population doubles, so our graph should also pass through the point 2, 4. And let's just do one more. At the end of day 3, this population size should double, and we should be up to 8 bacteria. So the model for this growth has to pass through all of these points, and there's a very basic function that accomplishes this. P of t equal to 2 to the t, right? So an exponential function will pass through all these points, and it's a perfectly suitable model for this bacteria in these conditions. But normally, when we write exponential growth models, we use base e. So let's come up with a model in base e. One way to get to that is to cleverly rewrite 2 using base e. So we can write 2 as e to the natural log of 2 and raise that to the t, right? Using properties of exponentials and logarithms, this is just another way to write the number 2. By the laws of exponents, this is e to the natural log of 2 times t. And if you use your calculator, you can come up with an approximation for the natural log of 2, like 0.6931. So here is a model for the exponential growth of this bacteria using base e. This is a more popular form for exponential growth. Base e is a more popular base because this number in the exponent that we multiply t by is an important number. It's called the relative growth rate. And roughly what this number represents is that at any point on this graph, the population will be increasing at a rate that's equal to 0.6931 times the current population size at that point. Those are ideas that are made clear when the student gets to calculus and they learn things like the derivative.